So this talk, How I Learned to Stop Worrying and Love Evaluations, although I should say I still worry, is I wanted to make this kind of one part like self-exploration confessional and one part motivational encouragement, especially for the students in the crowd who are maybe like thinking about what the future holds for you if you're planning on doing a career in research, in NLP-focused research, and then one part frame story of recent stuff that I've worked on. So let's start with the first two, which are, I think, more fun. So the motivational aspect is that in your research life, in your life in general, you should have fun and you should do good work. I'm specifically talking about research, not about, say, teaching or other non-research or other aspects of things. And actually, I'm even not going to even talk about the good work too much. I think that's relatively easy, honestly, if you believe that, doing NLP research and trying to advance the state of the art and trying to make novel contributions and maybe introduce some new exciting problems or explain old ones in exciting ways is good. And essentially, as a good metric, if you're gainfully employed, you're probably doing good enough work for some definition of that. But actually, and I think that there's some objectivity there, believe it or not. But having fun, it took me a while to realize, is actually more subjective, which you wouldn't think would be something I needed to learn. Yeah, it's finding out what works for you is really important, and that's kind of what really motivates this whole talk. So this is one way to have fun. I don't know if anybody wonders what this square is. I think of this as what you draw once you've proven something, right? And if you can do that, it's very, very satisfying, honestly. I've done it a little bit, and you get this sense of deep understanding when you really worked through something and proven something nobody else does. And honestly, there's kind of like this great academic tradition of that you should prove things, and that's very fun and satisfying, and that's okay. It turns out that usually if you're going to prove something, it's going to be about a very, very exceedingly small, narrow sub-detail, which is a little bit unsettling to me. Personally, I have a hard time doing it. It feels like pulling teeth in the very limited number of times I've done this. Also, I'm not a very good compiler of my own proofs, so I usually had to work with somebody else who would say, no, you missed something there. And so that, that's not a great way, and not a good scalable way to work. And then, I don't know, even after finishing it, I don't know, did I get it right? Maybe this is not a meaningful result and isn't going to have any impact, or maybe it's something that is very obvious or was proven 50 or 100 or however many years ago. So I'm not super. If you have fun doing this, you totally should, but I didn't have fun doing that. Another way to have fun is to provide tools for people. So that can be new algorithms that people can use, or some software, or maybe even a data set. And it's really nice. You put something out in the world and then you hear about other people using it and doing something with it that you never even envisioned doing it. And I've had a little bit of experience doing that too, and that's good. It's not so lovely when you have to actually support it and people come and say, hey, there's you had this bug, or like, can you add this feature? That's more of a software thing than an algorithm thing. It is nice to see when people like expand upon your work and improve it, and they've taken it to another direction. Although honestly, I feel a little bit protective, and I get a bit of a sense of loss that my work has now been passed by. So honestly, there is a bit of a negative feeling. And again, many people don't have that problem, and if you don't, that's good. And what I actually like is this. I like to sit at a computer and I type run baseline, I get a 32.4, and later I do run experiment and I get a 33.0. And honestly, even if I wasn't doing anything real, if you actually wrote a software program that just did that for me, I might be totally happy. I could just sit in my box, right? So I think of this as just hill climbing. And again, this is the thing where I think for a long time I was embarrassed about it. So this is the self-reflection part that I'm no, I'm not. I'm coming out and saying I like hill climbing. And it's a very satisfying. Again, if I'm working on a particular task and now I'm able to do it better than it has been done before, or maybe even better than I've done it before, using this new approach, or maybe just a twiddle on old approaches, or something that in retrospect is obvious, for me it's a huge endorphin rush. Just to see that number go up, I really feel good. There are risks here too, right? I want to know, maybe this was a one-off, maybe this can't be repeated. Maybe this result isn't really real, maybe I've accidentally moved my, looked at my test data too much. So a possible solution to this is to have a carefully conducted and fair and maybe third-party monitored evaluation, and that's largely what I'm going to talk about. Thankfully, at least those of us who work with the government funding agencies, there's people who have similar desires. This is a slide thankfully provided by DARPA about the overall progress in Arabic machine translation as a result of the Gale project. Here we're looking at error rates going down over time, over from phases 1 through 5 in a variety of different genres. And you can see that as a result of this project and several years of concerted effort and some money, the scores kept going better, right? We were able to make this progress in terms of getting that number better. And similarly in Chinese is a little harder. And so why were we able to do this? Well, I would argue that a large part of the reason that these programs were successful was because of competition. So here is another kind of, this is just Chinese to English SMS chat, but it's a microcosm of the larger thing. So here what we're seeing are, again, so this is now the accuracy, it's accuracy, so it's higher is better. And the details on this graph are not important so much, except that we can see that, so we want to be higher. The blue lines are BBN, which was the group I was a part of as part of ISI and as part of Language Weaver, and then the red ones were IBM, which was the other team. And so, what did we have in our minds when we were working on doing these translations and ahead of evaluations, where we really wanted to beat the other guys, right? And they probably really wanted to beat us. And that really helped. It really drove us. And then furthermore, so the dotted lines are phase 2 and the solid lines are phase 3. We really wanted to improve. We wanted to make sure that we were better than ourselves a year ago. And actually, even not captured on this slide, is that even within the BBN team, I was like, as Language Weaver, we got to beat those ISI guys, we got to beat those BBN guys, and that kind of competition, I think, has been helpful. And in other cases where there's not this competition, I haven't seen this kind of improvement. So it's not just scores, right? The result is translation has gotten qualitatively better over the years. This is an Arabic sentence and beginning of a news story from. That was translated by, I believe, Language Weaver software in 2002. And you can see it's pretty word salady. Insistent Wednesday may recur her trips to Libya tomorrow for flying. If you saw that, you probably had no idea what that means. By 2003, after hill climbing on stuff, this has gotten better. Egypt Air has tomorrow to resume flights to Libya. Still kind of chunky. And you can see the sentences in the paragraph are starting to be a little bit more sensible. By 2015, it had gotten really good. This is pretty close to publishable. There's definitely some conjugation errors and whatnot, but you could read this and understand what's going on. And it's more than just looking at these qualitative benefits. I mean, the improvements in machine translation software over the last 15 years or so has had real tangible benefits in the marketplace. So in 2002, I don't think you could have TripAdvisor doing what it does today, where people are writing reviews of places they go to all around the world, and then consumers who don't speak English can see those reviews and actually take action on them. You can't have a relationship with somebody whose language you don't speak halfway around the world. You couldn't do that back in 2002. You can do a lot better now. And that's not just true for machine translation, although that's what I'm more familiar with. This is a similar kind of graph from the Gale stuff, but this is NIST speech benchmarks over the years. And this has enabled technologies like Alexa and Siri to be feasible, viable, even though obviously there's still a ways to go. So for the rest of this talk, I want to try to convince you with some details that this participation in evaluations is actually fun. If you have a like-minded sensibility of me, and if you don't, you should do something else. Obviously, maybe it's better to draw boxes. And it's time well spent, and it actually leads to real progress. So we're going to talk about the Lorelei project, at least year one. It's a time-constrained surprise language exercise. I'm going to talk pretty much exclusively about the machine translation component, even though it's actually a bigger story with information extraction and a kind of distillation. And then in the second part, I'm going to talk about my experience on the other side of the fence, running an evaluation, and the lessons learned there, and the kind of the benefits from doing that kind of thing. So that's it. And now I'm going to move on to part one, which is participating in evaluations. So this is work that done as the ELISA team, which is a consortium of universities and companies, USC, ISI. We were obviously, that's where I'm coming from. Also, there's participation from Berkeley, Brno, University of Technology, a company called Next Century Corporation, the University of Notre Dame, Penn, and RPI. And what we're talking about here is doing translation put under some constraints. So a lot of the work that a lot of the funding for MT has been, and the efforts have not really worried so much about constraints, right? We've had a lot of data at our disposal, and we haven't had to worry too much about training time. So the Gale and Bolt projects, so Bolt was a follow-on essentially to Gale, those, we had on the order of 200 million words of data of examples of translations from Arabic to English or from Chinese to English to work with. That's a lot of data. The Europarl-based research, it's largely, I think, European funded. They have transcripts from European Parliament in multi-part translations and around 60 million words. So still pretty substantial. And if you're familiar with recent work in neural machine translation, largely here we're at the scale of 300 million words or thereabouts. So this is a big system, a lot of data, took a long time to curate, high resource, high availability, and largely doesn't really matter that it takes days or weeks to train a system. That's considered just a one-time thing, and afterwards we're going to have a well-trained system. And there has been work. There has been work in low resource or in fast training. These tend to be under, I would say, highly simulated conditions. You'll have a Spanish-English low resource effort, but we have a lot of Spanish-English data. You just take some of it, and there's your low resource. There's some bias there. There's some institutional knowledge about how you translate between Spanish and English. When you're really operating in a low resource environment, you might not have those kinds of biases baked in. There's definitely good work on training systems under a time pressure, a short training time. Of course, to do this work, you're not under a real time pressure, and I argue that does matter, actually. And then, of course, a lot of results papers, most results papers have many months of hill climbing behind them, as they should. You're trying to understand a scientific result behind that. But there is something to be said for working under a fast constraint and seeing how well you can do. And the reason is because we actually sometimes want to use our MT and other resources in a scenario where time really does matter. So a large inspiration for Lorelei was the Haiti crisis in 2010, when a large earthquake resulted in a big humanitarian crisis. There was, a lot of need for disease prevention, a lot of need for rescue efforts, and most people in Haiti spoke Haitian Creole, and most people who were in a position to provide aid did not. And so there was an effort to try to use NLP and IR to help with this. So there's been some reports on this by Will Lewis of Microsoft, Rob Monroe, who was at Stanford at the time, and Stefan Vogel from CMU. And they tried to handle. So there's a text messaging service put up where you could text your request to this number 4636, and people would try to respond. And there was a lot of human effort here, right? So the Creole-speaking expat community was enlisted, but also efforts were put in place to try to do MT, to try to do information extraction and sort of understand what was going on. There were successes and failures here, but this is not a time that you actually want to see, which team does better than the other, right? You want to just try to get it done as quickly as possible, not even worry about the NLP if you don't need to. So we want to simulate this. So we still want to be under time constraints and be able to respond in real time when something like this happens again. And that's what the Lorelei scenario is. Right, so the idea here is, okay, there's people, and they're in a nation that speaks a language that we don't have capability for, and then something happens, and we need to provide disaster relief. Maybe we have some capability in other languages. There's not a lot of people and not a lot of resources for Haitian Creole, but there is a relationship between Haitian Creole and French, and maybe we've got some resources for French available. Furthermore, there's maybe some language agnostic capabilities that we can build ahead of time, some linguistic universals that we can leverage when we have to work in a language that we haven't really worked in before. So how can we get up to speed going quickly? This little graphic is maybe a little bit hard to read because it was small to begin with, but it's from DARPA. The idea here being that before Lorelei, like currently, right, you need weeks or months to create a system. It costs a lot of money. It's not a fast throughput scenario. You're not really going to be able to be responsive in real time, and hopefully afterwards you will. So that's the aspirational goal, right? So now the question is, how are we going to evaluate whether or not we're able to do this? And the kind of common thread that has underlined most of my professional life is what is often called a bake-off. And the idea is, so I'm fond of the older show Iron Chef, where, which is similar to current cooking shows, like maybe the Great British Bake Off or Top Chef. You have a bunch of experts they're very good at their trade. They maybe each have different ways of doing things, and they're given maybe a set of ingredients, but maybe also their own capabilities, and they have to try to impress the judges after a certain amount of time, right? Also, much like these shows, there are eliminations and cash prizes, but it was less fun to talk about, so I'll skip over that. So what are the ingredients in our particular bake-off? Well, the idea here is, like in Iron Chef, if you remember those days, there's a surprise language that gets revealed suddenly, right? And a surprise incident. And we're going to get a little bit of data for that. And furthermore, we're going to get a medium amount of data for some other languages. Maybe some of them are going to be related to the language that we care about. So in this case, in this year one, we were given data for Hausa and for Turkish and for Uzbek. A key resource for machine translation is parallel data. This is examples of sentences in one language and their translations in another. So this is an example of some Uzbek and its translation. We also, furthermore, get some annotations. We might know that Karimov is a person, Salamlar is a noun phrase. And these can be useful in information extraction and in other novel ways of doing translation. We get a lot of monolingual data. So essentially, we're getting websites that have been mined and scraped, or discussion forums put into a text format. And those are provided to us. We get dictionaries. Dictionaries are a somewhat undervalued, I think, but very actually valuable resource, often in electronic form. And they might be from, say, your language to the language you care about to English, or maybe backwards the other way, or maybe into a third-party language. We get grammar books. So maybe get some understanding of the morphology of these languages, especially when they're morphologically rich. This is very helpful. Or some notion of word orders that we can try to exploit, either automatically or manually. A particularly novel ingredient that we get in the Lorelei project, specifically for the incident, is this notion of a native informant. So the kind of metaphor we tend to use is a taxi driver, which is to say this is somebody whose primary language is this incident language. They speak English, but it's not necessarily they're able to communicate, get along in English. They don't have linguistic experience necessarily, right? If you tell them like tag all the noun phrases, you'll have to explain that, which you would have to do if you talk to somebody who's not a linguist of any kind, right? And you have some time to talk to these people. Okay. So given all those things, now we have to also lay the ground rules down. So the ground rules are this. On day one, you're going to get this data pack where you have some parallel data, some monolingual data, and furthermore, you're going to schedule some time with a native informant, 1 hour. And you have a week now to produce a system. At 1 hour of the native informant time and the initial data and the data that you've been given ahead of time. We actually had a stretch goal, which was, can we actually produce a system in 24 hours? So after you submit your first system, you get a little bit more data. In this case, it's actually just source data. You get some maybe more information about the incident that's occurred. Now, and you have 4 more hours to schedule with the native informant and another week. And then submit another system and see how well you did. Then you get some more data, then you have 2 more weeks, and finally submit a third system. Okay. So since we're expert chefs, we want to make sure that we don't just come in there, and not know what we're going to do ahead of time. We want to come in on the ground running. So we actually have a basic recipe in mind. And this is what our basic recipe is all right, the data is going to come in, and we're going to divide it up. We're going to make some training data. So we're going to learn a system, learn coordinations between source words and target words. We're going to take some data for parameter fine-tuning. That's our tuning data, and some held-out data so we can see how well we're doing, evaluate. Furthermore, we're going to have a bunch of machine translation approaches in place. We had 4 different flavors. We had our syntax-based machine translation system that comes out of ISI. We had a visitor from a university in China who had a system called Neotrans, which more or less does phrase-based or syntax-based machine translation system. We have a hierarchical phrase-based machine translation from David Chang in Notre Dame, and his team also used Moses, which comes from Philip originally, I think in the phrase-based approach. So each of these systems can have different flavors, different parameter settings, and they're all going to produce translation systems, are all going to produce translations of the evaluation data. And then we're going to have to kind of combine those together and form one final translation. And we just use a tool for system combination. This is something called MEMT that was created by Ken Heafield, and that's going to be our submission system. So we're going to have that basic approach. I should note that the system combination needs its own special tuning and evaluation data too. Okay, so we realized that we're probably, at least at first we realized, okay, this is going to be our good core strategy. And we're probably going to want to deal with data a lot. And so as we deal with data, as we improve our training data, as we change our training data, we're going to propagate those improvements to the group. They're going to come up with more translations, and we're going to feed those also into the big system combination hopper. And so we're going to spend most of our time focusing on that. Also maybe changing our tuning data, also maybe changing our testing data. All right, so this is our game plan going in. And now comes the day, and we're all really anxious, and I got up really early in the morning because everything happens on East Coast time, and here comes the secret ingredient, big reveal, and the language is Uyghur, which is easier for me to say. So Uyghur is a Turkic language. It is most prominently spoken in northwestern China, Xinjiang province, which is an area of the world that is very subject to earthquakes. So the incident that was happening was there is an earthquake, and it happened in Xinjiang, and so get going, guys. Okay, so now the next step is open up the box and see what's inside your initial data pack. Okay, so what did we get? Well, we had some parallel data, and it wasn't really about earthquakes at all, which we anticipated. So there were 2 technical manuals, like maybe help messages from Ubuntu and GNOME. There was a short phrase book, and there were 15 copies of the Quran, all translations from Uyghur to English. We were able to have these massively multilingual resources ahead of time that we'd prepared, and we collected names from many, many languages. So we had about 1,500 Uyghur English name pairs. We also had some bilingual dictionary that was provided, about 150,000 of those. So from that data, we split things up into dev and test sets and system combination tuning sets. We kept the Quran out of those because we thought maybe optimizing towards translating the Quran was not going to be so great. Everything else we fed into training data. And we also had a gigaword language model. And so for our 24-hour system, we basically just had to run the game plan. We actually didn't even bother with the system combination. We just ran our syntax-based machine translation system. And so our stretch goal gets us to, this number, 11.85. So this is a blue score. Essentially, higher is better. It's an automatic way of evaluating machine translation. And so the idea is, can we climb from this hill? And furthermore, when we look at our test data, what are we going to see? And what we saw is, well, this parallel data is highly, highly out of scope. We couldn't find anything about earthquakes at all. And there was, of course, lots and lots of words that couldn't be translated. So we definitely needed to work on that. So now we're in the mix, and we actually have our week to work on. And we wanted to make sure we leverage universal tools as much as possible. Stuff that we didn't have to think about, we could just push a button and go. And one thing that we had was pre-prepared was this universal Romanizer. So the idea here is take any writing system and convert it into Latin text that tries to preserve pronunciation. This was built for us by Wolfram Jakob, who's a ISI staff member. So this is a sentence or an entry from Wikipedia. It's different ways to write Singapore. If you feed it through, you get something like this. Some is not so great, like Kangapu maybe isn't great. Sinjapu seems better. Anyway, this uses information from like the Unicode tables and some heuristics, and Ulf worked and improved it. Actually, this is, I think, publicly available. This is very helpful for us because Uyghur is written in Arabic script, and most of us can't read that. And he actually would adjust it during the evaluation to make sure that it got every little Uyghur word correct. Okay, so we wanted to improve our vocabulary coverage. A great source of vocabularies is dictionaries, of course. That's what they're all about, is improving vocabulary coverage. So they could potentially be used as training data. But they tend to be not super usable for machine translation in their native form. So if you have a sentence and its translation, that's great. Machine translation systems really know what to do with that. If you have something like this, so this is the left side is fed through the Romanizer, like Hesse, and the translation is share, comma, portion, parenthesis, e.g. 1/3. You don't want to feed that directly into an MT system. It doesn't know what to do with it, right? As a human, oh, this means either share or portion, and an example of that is 1/3, right? So we need to automatically process like this, right? Another problem with dictionaries is you have things like Bagban, si Bagwen, right? So you have these cross-references. Again, not super useful in its native form. So you have to detect, this is a cross-reference entrant, and if you see Bagwen is gardener, then Bagban is also gardener, right? So we had to come up with some approaches for doing this. And actually all we really did was we had a guy, I had written some small rules on this, and we had an intern who really tried to expand and kind of hill climb on this. Another aspect of dictionary processing that's important is morphological expansion. So if we see that Franzier is France, That's fine if you see that word by itself, but you might see franziette or franzietta or franziette in this morphologically inflected language, which translates variously as at France or in France or on France. And so it's important to generate these forms and expand your dictionary that way. So this was the purview of our summer intern, Sebastian Milka, who, by the way, has applied to JHU. He also applied to USC, so, we should fight for him. But anyway, he's a good candidate to look out for. And this was largely just really, in this case, was a grunty effort, right? Is rule-based and just trying to make these things look good and using human intuition. And this is an area in which we would like to automate in the future. So another kind of nitty-gritty approach was covering certain classes of phrases that are relatively easy to write rules for. So like translating numbers, translating dates, translating quantities. And Ofram Jacob had built a fairly flexible system that requires you to write a few regular expressions and then will feed into a abstract date language processing approach. So if you have, for example, this rule that says if you see the numbers 1 through 12, maybe followed by some spaces, maybe followed by some punctuation, and then followed by eining or I, that should translate to month, that number, which is an abstract date language. And if you see month 8, then you look that up and make August. So these kind of nitty-gritty approaches that you could work on and hill climb on in a week led to plus the system combination and dictionary expansion led to a healthy increase after 1 week of hacking. So that was good for week 1. Then we wanted to get a little fancier in week 2. So we started focusing on, hey, how about these related languages that we were given? We were given Turkish, we were given Hausa, which is right out, when we were given Uzbek. And turns out Uzbek, very close to Uyghur. So here's a sentence in Uyghur/Uyghur. And then if you pass it through the Romanizer, this is what you get: Washington'da, Birkancha, Muhim, et cetera, et cetera. And then if you look at the same sentence in Uzbek, it turns out they're really, really close to each other, except for maybe one word. Everything else is basically a cognate, and the word order is the same. In fact, when we talked to the native informant about this, they confirmed, yeah, Uzbek is actually 80% intelligible. So we wanted to say, okay, could we leverage this data? Could we convert the Uzbek data into Uyghur? So the first thing we tried is, well, we could take the Uyghur and then Romanize it, of course, and then maybe remove the vowels, because the vowels seem to be where things differ. And then do that also for Uzbek, and maybe that'll allow us to increase our training data. So we would take this sentence, Washington to Birkancha, convert it into Latin script, and then remove all the vowels. And then you do the same thing with the Uzbek, and you get Vishington Birkinch and Washington Birkinch, yeah. And then 2 out of 3 words seem to match, so that's like, sign of life. Turns out, let's just first see what does this conversion process do to your Uyghur data for actually translating. If you just take the Uyghur data, forget about the Uzbek for a second, and do this processing, already you're down 3 or 4 blue points, which means you've got to make that up plus more if you want the Uzbek to be useful, so not a good solution. Better solution was try to convert the Uzbek directly to Uyghur. And to do that, we had dictionaries. So we had dictionary entries into English for both of these languages, so you could pivot between the two. And that gives you a table of Uzbek Uyghur translations. Furthermore, you can learn similar kinds of dictionaries using Giza, which is an unsupervised way of basically essentially building small t-tables from parallel data. Yes, Kevin? Probably less the romanizing and more the vowel removal. And the vowel removal is pretty critical in this case. So anyway, build big dictionaries, build dictionary-like things with Giza. Again, using some off-the-shelf software, DirectTL plus some hacks afterwards to try to come up with an Uzbek to Uyghur converter. So that was helpful in expanding our data. So now another thing, we haven't talked about this kind of secret ingredient, which is the native informant. Right? So a lot of work with humans in the loop uses simulation. And simulation, can only kind of go so far. Right? When you're really interacting with a native informant, you have real-world issues. So there's the language barrier for instructions, right? And this is not just the fact that you're talking to somebody whose L1 is in English. This is talking to somebody, you have to kind of explain maybe what a noun phrase is or what you need for out of a translation. There's typing speed, right? And just maybe a hesitation at trying to get a preposition in English right. There's interface hiccups, maybe we're on this system that's kind of like Skype. It goes down. You have to kind of keep up the flow. You have the time you have. There's also social graces. This was pointed out to me when we would sign on for our native informant session. And I'd say, hi, okay, could you please go to the Google Doc and open up this tab? And they were like, John, maybe you should just say, how's it going? How's the weather? That helps a little bit. You got to do these kind of things, even though it takes away some of your time. So what did we do with our native informant, right? We asked our native informant to translate some term lists for us. Maybe we thought these were earthquake-oriented term lists, which this was fairly fast of the native informant to do. We're not really sure how much that helped. These were just small phrases. We had an English description of this incident, and this was important because we didn't have much earthquake data. So we asked them to translate from the English to Uyghur. Translation by humans is fairly slow, even for good translators, I think. So we got about 360 words an hour. It's just, when you're watching, it seems so painful. And furthermore, when you're going into Uyghur, the quality is kind of unclear, right? We don't know if they're doing a good job. They just produce something for us, right? We did also have them do some translations from Uyghur to English. One point here I want to say is that at first I just tried, okay, please translate this sentence, and then we would watch them translate, watch them worry, is this word for, is it to? Make errors that I was like, okay, I know how to do this. So what I realized is a much better way is to have them work on the adequacy and have us work on the fluency. So I would say, okay, can you tell me about this sentence? Let's talk about this article. And I would just type the sentence, and then they would be able to read and say, no, that's not what I mean. But I didn't have to do post-editing this way, and it shortened the time, and it was just also much more satisfying, I have to say. I think both sides, we get to learn about politics and everything like that. We also post-edited our human translations from Uyghur to English, which you might wonder, wait, what? How are we able to make our own human translations from Uyghur to English? Well, we had another secret tool in mind, a thing that we call somewhat erroneously the Chinese room, after the John Searle thought experiment. The idea here is that we wanted to see, could we be translators ourselves? This actually was originally created to see, could we be machine translation systems ourselves? So we want to make the native informant's time more efficiently used. So we wondered, could we do our MT given the same resources that we give to the MT? So if I'm given a bilingual corpus and I'm given a parallel, I'm given a dictionary, and I'm given some I have my own knowledge of what English is and reasoning and external knowledge. Could I create translation sentences? And if we do, well, we can make ourselves this Uyghur English corpus. So we have this tool, which we call the Chinese room tool. Again, created by Wolfram Jakob. And the idea here is at the top, you can see a sentence, 2011 Yildiki Yaponiye Er Terwesh Wed Dengiz Tashkini, run through the Romanizer. Very helpful, of course. And what would happen is when you click on a word, it highlights in red, and then you can type in your gloss, and it just goes up in green. And it's really just a note-taking mechanism. At the end, you can type in a sentence gloss. But importantly, when you click on the word, below this bar, you can see there are dictionary entries that try to match the word and the engrams around the word that you selected. So you see Terwesh, and here, okay, cataclysm, earth tremor, earthquake, earthquake zone, earthquake intensity. We can see that clearly Terwesh means earthquake. Grammar clues, they might be helpful, they might not. In this case, this is trying to match a prefix to a suffix, the te, so not useful. And then here we can see Teret Kuch and Toreryadut, not a match of Terwesh, but we can see that probably goes to oscillator. Teryedu probably goes to tremble. So you're definitely getting something about earthquakes in there. And we're able to intuit this, right? I was able to intuit that by looking at this. And we're able to then create something and then have the native informant post-edit for adequacy while we do it for fluency. And this ended up being very useful. By doing these two things together, we built about a 1,600-word corpus. Small, but respectable given the amount of time. 19 articles. The 19 is pretty high. It's probably mostly tweets, and then like one or two, like 5 to 6 sentence articles. I do have a little frowny face here. So time is precious. This resource is super valuable. We wanted to use it to optimize our parameters, specifically in system combination. We also wanted to look at it and see, okay, how well are we doing on this set? So we did. We're risking overfitting, but c'est la vie. Okay. Turns out, good idea. So this graph shows in the x-axis the blue score of this domain set that we created for the various systems. Each of these dots is a system that we ended up submitting. Domain was all we had to go on, and so we said, okay, the one that scored the best in domain, that's the system that we think is our official submission, our primary submission. The y-axis shows us we were given in this particular evaluation evaluation set scores. Good relationship, right? Good idea. If we had used our original test set, which was about things that like some phrase books and some Ubuntu manuals, not a good idea, right? So there's no good relationship here at all. Okay, so that 1 week gives us over 2 more blue points. Bigger dictionary, domain hill climbing set, the Uyghurized Uzbek English. So the domain is super helpful. At this point, I was getting a little bit annoyed because I had a lot of different systems together, and I was the one who chose which went into the system combination. So I'll get on that in a second. But we wanted to, of course, make our data better, keep on doing what we're doing. So now we're going for the last 2 weeks. So it turns out we had not used this before. There was a big data set of domain-relevant English. We incorporated that in our language model. Hill climbed on the Uzbek to Uyghur by using Wikipedia entries and Uyghur monolingual data. Ulf hacked on the number and date rules, made them better and better. More dictionary entries, better dictionary entries. We made another domain set, this time without the help of the native informant, which made me a little bit skeptical of it. Okay, but now a system combination. So I've been basically saying like, okay, well, I'm going to take one from column A and one from column B, and this guy did well before, put them together, run the dice, and see how our scores are on a domain. It's kind of frustrating. And so we realized, and putting them all together, so the particular system combination system doesn't scale very well with a large number of systems. And furthermore, if you have like a lot of bad systems and a lot of good systems together, it just kind of gets confused. So didn't have time to optimize that or hack on that. Instead, we said, well, what if we just try all 19 choose 3, we had 19 systems at the time, 19 choose 3 combinations, just throw them in, and then plot on the domain score on the x-axis and this domain 2 set on the y-axis. This yellow thing was what I did manually beforehand, which I have to say, not bad for a human, right? But the nice thing about this is we had some confidence about this kind of convex hull pointing towards the upper right. And we took the systems that were involved in there, and then when we had a few more systems, we would recombine with those and recombine and then do the same thing over and over again. And really kind of we could push out towards that upper corner, and then we were able to choose from that convex hull in terms of what we submitted. Now, I should say that I let my human instincts get the better of me. I was worried about overfitting on domain, but I was like, well, domain worked so well in checkpoint 2. So I just used more or less what we did best on domain. Turns out our best system in terms of score on the eval blue was not the best one on domain. We clearly had overfit on domain by then. Domain 2 is a little bit better. We probably still wouldn't have gotten to that green dot, but should probably trust the other domains. So by checkpoint 3, we got to another almost a blue point by adding dictionary words, by adding this hill climbing test, by changing the way we did system combination. And so that's where we got to by the end. This is a qualitative example of how our machine translation improved. So you can see the source and then the romanization, so you can pronounce it. And now the reference, 180,000 hectares of land have been damaged. Assistance worth $4 million has been sent. 24-hour system, not so great. I mean, you can see harmed, 180,000s, but who knows what a guitar lick is at that point. Checkpoint 1, getting a little bit better, but it's still pretty kludgy. I would say by checkpoint 2, more or less the content is there. Checkpoint 3 improved things a little bit. So in conclusion to this part, our key components, right, okay, this in-domain data, this was the crucial thing, building that. And using the native informant and the Chinese room together, very helpful. Processing the dictionary is also important. Big liability is that we had to basically rely on a guy hacking this. And so improving that and automating that is a really big thing. And we think the related languages are good too. A minus of this kind of evaluation-based, time-sensitive thing is we didn't really get a chance to tease apart how much did this part help? How much did this other part help? And so now is the time to go back and look at those things. All these things required some manual effort. Having universal tools is available, but I argue that there's a lot of lessons learned here that we wouldn't have learned in a more synthetic situation. We were just synthetic enough, I think. Right. So that's all I have on the Lorelei part. I'm going to move on to part 2, but I wanted to pause and see if there were any questions about the machine translation stuff before I go on. Yes. Mm-hmm. So they have more data now?
Yeah, so they just said, well, this sucks, so we're just going to
right.
Effectively, they said that low resources are more important.
I would argue that's the wrong approach to take. The fact of the matter is that sometimes you have low resource. Sorry. It's not the wrong approach to take. It avoids a problem and finds a different solution to a different problem.
Yeah, I have nothing all that deep.
Yeah, I would say that inspires that, we're really great pattern finders, right? And we're able to do it with shockingly low resources. And computer's not there yet. At least I haven't seen it. All right, let me move on to running an evaluation and a completely different data set. And don't worry, this part is short and can be skipped through as we get close to the end. We got about 15 minutes. Okay, so now I'm going to talk about abstract meaning representation. And not necessarily, okay, if you don't know what abstract meaning representation, or AMR, is, this is a graph formalism that provides semantics. It's English biased, not an interlingua. And it is intended to be applied to whole sentences, give a whole sentence logical semantic coverage. It grounds itself into existing semantic ontologies like prop bank, and also grounds its named entities and other things to Wikipedia, I think just named entities. And most important from my non-semantics space perspective is that we have a decent amount of data. So we're moving away from super low resource now. We had, at the time of the work that I'm talking about mostly here, about 20,000 sentences annotated with AMRs. Now there's about 40,000. And there are definitely some, there's lots of things that you can argue about problems with AMR. I'm not really the right person, unfortunately, to defend them, just because I'm not an AMR person. I've just mostly been using it as a tool, or looking at the problem from the kind of corpus-driven evaluation process. But we can talk about it too. Okay, here's an example of an AMR. Here's a sentence: George Washington was not afraid of dying. What we see here is there's a fear 01, which is a particular prop bank role. Here's some negation. We're saying that this fear is not happening. There's a person, and that person is fearing. That's what arg0 in this case means. Furthermore, that person is fearful of being the target of dying, being a thing that dies. So there you have this person entity that's playing multiple roles. And this person's name is George Washington, and is tied to a Wikipedia page, George_Washington. The goal of AMR is to abstract away syntax, so that the soldier was not afraid to die is equivalent to the soldier was not afraid of dying is equivalent to the soldier did not fear death. It's more or less the same AMR, except I took out the George Washington parts. You can represent this in multiple ways. There's this picture below that kind of looks like a figure person, and then there's also this Penman notation, which we used before, showed before, which is good for computers to read and process. And then there's this a conjunct of tuples, which is very helpful, as we'll see in a second, in scoring. So there's all these things are true at the same time. So these are all semantically equivalent. So if we had the ability to take an English sentence and produce an AMR parse, we would get this integrated semantic analysis for full sentences, right? So Kevin Knight likes to say, once you're on top of this kind of semantic hill, you have maybe newfound perspective. You can do sentiment analysis. You can you have any kind of preprocessing for downstream applications. You maybe can cluster different sentences in different ways. In much the way that we use syntactic parses to create syntax-driven string to tree-based MT, you could create string to semantics-based MT. So the availability of this corpus, no surprise, led to a flurry of parser papers, and also claims about how well the parsers were doing. So there was this Artsy et al. Paper, which is a best paper winner at AMNLP in 2015. There was a paper from ISI, also at AMNLP 15. The one cites the other, but the numbers don't necessarily line up. There's also a Wang et al. Paper from ACL 15. There's a lot of confusion. Different data sets are being tested on. Not a very clean room environment. We also had in 2015 a lovely Dogstool seminar. Now I want to take a break actually and say, before, I've been in this game since more or less 2001. I had not heard of Dogstool beforehand. Apparently I was supposed to. If you have not heard of Dogstool and you get invited to one, you should go at least once. It's super fun. You get to go out into the middle of nowhere in Germany, into this lovely chalet. You drink wine. You eat a lot of snacks. It's a very nice open environment, lovely countryside. Talk about a particular problem for a week. Donald Knuth has signed all his books. They're in there, and you talk about stuff and maybe try to solve a problem and maybe write a report about it after the fact. Anyway, if you like taking trains, you need like 3 trains to get there, so I love that. In this case, there were the formal language people, people who work on like graph automata and tree automata, and also natural language people got together to try to think about parsing AMR with graph automata. So we had these tutorials on these esoteric-y things like hyperedge replacement grammars and directed acyclic graph automata with statistics added in, and we did some semantic parser code hacking, and it's cool. I actually thought my favorite part was just the part where we sat down and tried and hacked the parser and tried to make the scores get better, no surprise. And I thought it would have been cool if we were all trying to compete. So I don't know that we necessarily learned all that much, but the takeaway that I got from this was, hey, wait, we should have a SemEval. So in the middle of there, I just emailed the SemEval people, and they gratefully let me in. So that was money well spent, I suppose. So the goals of this task were to do a clean room head-to-head comparison of AMR parsers using test data that nobody had seen before, gather all the scores together in one place, and then compare and contrast different approaches. And so the lessons learned are maybe a little bit different and a little bit more low level, and hopefully not too boring. But so it's important to actually talk about how you score how well you're doing on AMR parsing. And this is using a thing called SMATCH. So far, this is the way that most things are scored, or maybe it's not the end of the story. But let's assume we have 2 AMRs. The one on the left is the boy wants to go. The one on the right is the boy wants a football. Clearly, these are not the same, but we want to know how not the same are they. So these can be represented, again, as conjuncts of tuples, and then we just try to match them. Look for an F measure. Assume one of them is gold and the other is hypothesis. And so we can say, okay, well, clearly they have a want. They both have a want-o-1. I should note one has an X want-o-1, the other has an A want-o-1. Those are just internal variables, and you shouldn't be penalized for getting those names wrong because that's totally internal to your own tree. They both have a boy. One has a go and the other has a football, so that's clearly a miss over generation. But then you have to worry about these arg0s and arg1s that are bound to these variables. And there's the question of, so what does this arg0 match to? If the arg0 matches to the arg0 on the left on the bottom, the consequence of this by following the chains of variables is that the arg1s don't match. And if the arg0 matches to the one on the top, the consequence is that the arg1s do match. So it turns out it's NP hard to find the optimal matching here. And the result, so what SMATCH is it's F measure with some heuristic hill climbing, where you start off with all the things that you know, and then for all the things that you don't know, you try something, and then you flip a bunch of bits and hill climb until you get to the best possible position you got to. Okay. It is case insensitive, so we don't care about our capitalization. It's of course, variable name insensitive. Also supposed to be quotation mark insensitive. This is the low-level detail that I'll talk about later. Okay, so running this competition, we did the obvious thing. We gave people AMRs. We let them train a system. And then I thought it was very interesting in the analysis to see, okay, where are people making mistakes and where are people getting things right? So here's a sentence, but now many are openly talking about the prospect of bidding him farewell. And it was not obvious to me, because I'm not an AMR person, that this is an instance of a contrast 01, right? That's what that top thing is. Turns out 7 out of 11 systems got that right, which means this is probably well represented in the training data. So nice to see that that happened. However, nobody got right the fact that the many are both talking and bidding. And so nobody got those dual roles right. Turns out dual roles, really hard to get right. Maybe shouldn't be a big surprise, but this kind of bore it all out, and we were able to see this in a very clean line-by-line analysis of all of this data.
Is it actually completely uncontroversial that the subject of bidding is bidding?
That the subject of bidding, the prospect of many bidding, again, not somebody who can really argue AMR with you, so I don't know. Do you think it's not? You don't think there's not a gap there?
It could mean that if you're talking about somebody leaving the government, it might be many people in the population that are talking about the prospect of the government or the party bidding them farewell.
Ah, I see.
So many members of the party are talking about the prospect of the whole party bidding.
So I don't know about the details about whether or not these are so these are supposed to be single sentence annotations. When you have this kind of case and it's unclear whether, so clearly if you had context you would be able to answer that question a little better, I think. And I really got a punt. So this is a good question for Kevin or Nathan Schneider, or really Ulfram Jakob. Right, you'd think that you could maybe do that. Anyway, this is a grounding issue here. So Kagan got SCOTUS in return for covering for him at Harvard. So in order to get the Wikifcation here right, you need to know that Kagan means Alina Kagan, and SCOTUS means Supreme Court of the United States, and Harvard means Harvard University, right? So 2 out of 11 get Kagan. This is probably means that Kagan and Elena Kagan, no surprise, was not well represented in the corpus, which the news data probably dates back to prior to her nomination. 5 out of 11 got SCOTUS. Oh, by the way, so the reason that 2 did is because they have external wikifiers, and they were able to mine Wikipedia, perhaps. 5 out of 11 got SCOTUS. So maybe there is some data represented in there, and 7 out of 11 got Harvard. Almost certainly is their data there. This last one was a real bear. So we can read that that says media advisory, but it's really literally these capital letters, each separated by one space. And so like tokenization just, screws everybody over. So this is Adviso 1 media. Nobody got that. And, maybe we should say they shouldn't, but, we can do it well. Can we convince the computers to do it well? Well, to the degree that we can't do this, that's why Mechanical Turk is still around. Okay, so what did we actually give people? So there's about 20,000 AMRs in the training data. A subset of them were these kind of weird set that are like consensus. They were created and people argued about them, or some kind of like fake examples that were guidelines. I don't remember what WB actually means in this case. Then about a little, like maybe 60% of the remaining were Newswire and 40% discussion forum. And about those ratios were held for the evaluation data, but about 1/10 of the data. We made tools available. I think it's a good idea if you want to lower the barrier to entry, which is important when you're not actually paying people. So we gave Cammer and Jammer, which were really robust, easy to download, easy to use systems. Cammer coming out of primarily Brandeis, Jammer out of CMU. We had from ISI a Word to AMR aligner, which maybe is helpful to some people, and then a SMATch script, which kind of kept on changing versions, more in a second, and a Python library from Nathan Schneider. So important thing to do when you're running an evaluation is run a dry run. I wanted to do this to test the procedure. Have teams decode the test set for the training data, submit results, score them, right? And so what we got is these. I would never have put a parenthesis as part of the name for Iran, right? But somebody did, and it turns out that messes up the score, and I didn't know that because I had never generated a parenthesis in a name. So it's really helpful to have a lot of different people's different kinds of AMRs. Very, very helpful. So, okay, SMATch 2.0, not robust to parentheses. So, and then the participants found yet another bug, and we got to 2.0.2. Turns out, I have to take blame. I fixed the 2.0.1 and 2.0.2. I no longer remember what the bug was. That introduced a new problem where like quote Iran and lowercase Iran, which should be the same according to the AMR standard, mismatched. Turns out of the 11 teams that submitted, only one of them was affected significantly by this bug. But it's a good thing I had 11 teams submitted, because if only 10 submitted, we never would have found this bug. So really good to have a lot of teams submitted. Makes your tools more robust. Okay, these were the final results, the official SMATch scores. And so the takeaway here is there were 2 teams. So there are a bunch of teams that are in the 0.6 range, and they all mostly have C's on them. And I'll say why in a second. This one team that got better once we fixed the bug got into 3rd place, and they were not a C team. But we wanted to I said ahead of time I'm going to give a trophy to the winner. And so I ended up having to give a tie. Unless you think I'm being metaphorical about that, no, I actually went out and bought AMR parsing trophies. So if you join SemEval, you too can win a trophy. When doing an analysis of the techniques, turns out, okay, so 5 of the systems were camera-based and 2 were jammer-based. And so, making systems available means people can have a low barrier to entry, and that maybe hurts your diversity a bit. Most of the camera systems more or less added like a feature or 2. There was one mostly neural system, which we had not heretofore seen. There was a system that came out of the Dogstuhl ideas. This is using synchronous hypergraph replacement grammars. And then there are 2 old school pipelines, completely statistics free. One didn't even look at the training data. They didn't score very well. Okay, so to conclude, I told you this is a short part.
Can you tell us how the other system? You just said the one that did badly.
Oh yeah, so the dynamic power and the meaning factor is the 0.37 and the 0.47. And then 0.44 is the synchronous hyperedge replacement grammar. So don't like to shade too much, but yeah.
Which was the neural system?
The neural system was the one that got up to 0.61 once the bug is corrected. So they did pretty well. That's from University of Colorado. Okay, so yeah. So this was really good for for seeing a good spread of approaches. It was really good for correcting your bugs. And it was nice to see at least some systems, one system that was not related to those camera systems that did pretty well. negative is that we didn't really get a big breakthrough, but we're undaunted, we're going forward, and we have a SemEval in 2017. I encourage you to submit if you're interested in AMR parsing. As you can see, a very low bar to entry, but if you want to do something novel, maybe spend a little more time. It's going on right now. You can already participate in the dry run. We're changing things up a bit. Now we have a domain adaptation aspect to things. We're doing parsing of biomedical text, PubMed cancer pathways. Pretty difficult stuff to read, actually. We've got about 6,500 of those AMRs and now almost 40,000 general AMRs to help you. And we're going to score with hopefully a not so buggy smatch. And then a totally new text subtask, which is text generation. So we give you the AMRs, you give us the sentence back, which is going to be totally crazy. And we'll do like a little bit of blue scoring, but the real evaluation is going to be a human eval. We're going to use the appraise system, which comes out of WMT. Thank you very much for everybody who's worked on appraise. So lots of fun and interesting work to be had in evaluations is my overall conclusion slide. And I think having the time crunches and having the data crunches makes things more real world, I think ultimately more useful in that direction, which is less well evaluated. And I think it's a great idea to host evaluations. You really get some experience of what it's like on the other side. And it's also good for breadth first exploration. You can see what a lot of different people are doing and do that kind of comparison. So I should have inverted these slides because this is going to go up too fast, but I wanted to thank a ton of people who helped in the Lorelei part on the above and the participants and helpers out in the SemEval part below. So this is going by very quickly because I want to put up a ad slide at the end, which is to say that I encourage you to join in at ISI and also in SemEval. Go to my website, johnmay.net, when you'll see links to signing up for your summer internships. I think those are due in early January. If you're a grad student, we pay well. You get to live in the marina and be at ISI. You can also stay for a longer period of time as a postdoc or even an actual job. We're hiring there. And I don't promise that you get to come to ISI if you participate in SemEval, although it wouldn't hurt. So please join in on the task and tell all of your friends about it. 1 o'clock precisely. So thank you very much. Yes?
There's this tension in evaluations between really pushing the science and just trying to maximize your score no matter what.
Yes.
For example, in TAC, where you have to build a graph of entity relations, and one team found that by splitting certain entities apart into two different entities, completely random, improved the score.
Yeah.
But there was no basis for that in the science. How do you think we should try to manage that in the evaluation?
So I think my first thought is I think there's at least two different issues raised by that kind of finding. One is that maybe your scoring approach is wrong, right, and needs to be tweaked, and this is a great way to learn that. Or like your parameters have been tweaked. I remember, I think from, I want to say the ACE days, that the first time people discovered, oh, why don't we just run it through Google? And they're like, okay, no more running through Google, right? So, they added that parameter later on to just kind of constrain you and see what do you do if you tie that hand up. So there's that aspect of things. But then there's the case where doing something dumb actually makes a tangible difference in the world, right? So, and in that case, yeah, you're not learning anything necessarily scientific, but we do have a strong engineering component to our work, depending on what your task is. And there, I think you're learning that a simple dumb thing helps. And I think so. Both of these have space to grow. But I agree that you definitely want to combat playing silly games. Marjorie Freeman from BBN, former colleague, I was pitching this talk to her, and she said, yeah, well, I agree mostly with you, but I think it's actually better to do internal evaluations. And because if you're doing internal evaluations, you can you'll quickly come across the ways that you can do dumb stuff and then quickly correct stuff. And you can't do that so well in an external evaluation. Money's on the line and everybody's coordinated, right? You have to make those changes much more slowly. So I think doing both is helpful, right? So you have a fast evaluation set and then maybe a slower one. Overall, I would say that this is just all part of the learning process, one way or another. So, yeah.
So this is a closely related question, I think.
I should just preface this by saying I think shared tasks are great for many reasons. One being that you can amortize the construction of resources over a lot of researchers, and also people can get ideas from each other, which is good. There are obviously downsides to shared tasks. One is maybe there's diminishing returns if people are working on the same task, and one might not always believe in the task. Some DARPA program manager came up with a task and a metric, and as somebody who likes the experimental section of a paper most for its ablation studies, which telling you why certain things worked and how much they helped, I wonder, how do we get best practices out of a shared task, things that might transfer to other systems and other tasks?
Yeah, well, I mean,
so if you really believe in the task, you just want to, as Jim said, you just want to get performance out of it.
Obviously. So for shared tasks like SemEval, of course, you have your results papers, right? And you have reflection after the task is over. And in fact, what I have is everybody's results. And so I was able to, I hid those from this because it was a little bit too boring for this talk. How well did people do on just instances? How well did people do on just attributes and relations, right? And as far as something like Lorelei goes, well, you had your task, and now we're going to go write our papers and submit them to our conferences, and we will see the effect of Uzbek. We will see we can maybe see the relative quality of building a corpus using a Chinese room versus use of native form. That's not a great scientific finding.
I'm not there. Of course, you put the ablation studies in the individual.
Yeah.
But I'm going to repeat the question about how do you get to best practices. So you've got 11 papers out of this.
Oh, specifically in the second part.
What did the whole exercise learn about how to build systems like this in the future? There's another way to use shared tasks, which is somebody has a hobby horse, like some particular typographical model or neural net architecture or something that they think should be used to solve all the problems in the world, and they throw it at this problem as an example of what you can do out of 5 and 24 hours. And that's also a good use of shared tasks. But often those are not the systems that win. And so the question is, what are the takeaways about how to solve NLP in general?
I think that the way you get this, I don't have an answer to what are the takeaways of how you solve NLP in general, or even what are the takeaways and what are best practices necessarily for AMR here. But you have all this data, right? You have the descriptions of what went into them. You find, for example, that the SHRGs were terrible overall, but if you dig in, you see that they did much better in this let's say multiple parent resolution, right? So you coordinate the task, the approach with the thing, and then from there you then conduct your subsequent study. So it's kind of like a scatter shot, right? It's a big shotgun blast. Some things failed miserably, some things did great, some things succeeded in a narrow point, and now you've got you can pick up the pieces and put them together in now a new best practices. You can even system combine them if you want to, just say, okay, we're going to just do a bunch of things and see what shakes out. I think that's what you have. You have the ephemera from the task. You have all of the scraps remaining on the floor. And I think without having that if you otherwise just had Yoav go and do his thing and we go and do our thing. Maybe we're like, these numbers weren't as good, or these numbers were terrible, so we're just going to leave it. But I don't have the sentence by sentence comparison. I don't have the assurance that we did everything all together at the same time. And having the shared test together, I think, gives you some more assurance about maybe what the numbers mean, and just gives you some more assurance that people were working in the same thing at the same time. So, it's the best I can do. Okay, hearing nothing else, thank you very much for coming.